Hello and welcome back to this session. In the previous session we had seen how we can connect a single switch to a microcontroller pin, and just to reiterate and also talk about the debounce activity using software. If the switch is as you see in this slide I have already drawn, if the switch is not pressed then it will give a logic 1. When the switch is pressed it will give logic 0, but when you press the switch will bounce, and how to handle that in software is what I am going to just write here again. So, you are going to wait till, so let me call SW switch is equal to 1. So, if you wait while switch is till the switch is 1, that means you are waiting for the switch to be pressed. The moment switch is becomes 0, you are going to get logic 0, you are going to call a delay for, we had mentioned say about 1 millisecond. Then after you come back from the delay, the switch will give you a logic 0, because the duration of time for which you would, a human being would press a switch would be significantly more than this. So, you are going to wait for the switch to be released. So, wait till switch is equal to logic 0, and once you find that the switch has been released, you will get a logic 1 again, but it will bounce. So, you are going to delay for again 1 millisecond. When you come back from the delay, hopefully the switch would have logic 1, and now you can go back with the understanding switch has been pressed and released, pressed and released, and therefore thereafter you can do whatever you wanted to do in response to this switch being pressed. So, all this will become part of your software as a debounce activity. Now, we have seen how one switch can be handled by the microcontroller. Let us now see, if you have multiple switches and you do not have individual pins to connect to each of these switch, how are you going to handle large number of switches, and that is handled by connecting these switches in a matrix form. One, the argument behind the matrix is as follows, that you would create a row and column. Let us say I create a row and column of 3 rows and 3 columns, and I connect 3 resistors which are pull down resistors, and these are going to come, the columns are going to come from output pins of a microcontroller, and these rows are going to go to 3 pins which will have to be programmed as input, and at the junction of each of the row and column you would connect a switch. So, what you have seen is that using 6 pins, 3 configured as output and the rest 3 configured as input, you are able to connect how many switches? 9, and this scheme can be extended to cover or connect large number of switches to a microcontroller system. Let me show you a better drawn diagram so that we can discuss this technique further. This is the matrix of keys. Here we see the microcontroller we have is a MSP 430, let us say MSP 430, and 3 of these pins P1, P2, P3 will be programmed as output. The other 3 pins here P4, P5 and P6 will be programmed as input, and we see that P3 is connected to these 3 switches S1, S4 and S7 to one end of these 3 switches. P2 is connected to S2, S5 and S8 here, and P1 is connected to S3, S6 and S9. Similarly, P4 is connected to the other end of S1, S2 and S3, and there is also a pull down resistor. P5 is connected to S4, S5 and S6, and there is a pull down resistor R2, and P6 is connected to S7, S8 and S9 with a pull down resistor. Now, you need a bigger software subroutine to handle this activity. So, this read keyboard function, let me describe it here. We'll call this subroutine as read KBD, short for read keyboard. This function will be called by the microcontroller and it will perform the task of identifying if any switch has been pressed, and if a switch has been pressed, what is the code of that switch. Now I have brought this diagram here for easy reference. We know that port pins P1, P2, P3 have been declared as output pins, and port pins P4, P5, P6 are input pins, and there are three pull down resistors R1, R2 and R3. So at the beginning of the subroutine will set P1 equal to P2 equal to P3 to logic 1. And then it's going to read the value of port pins P4, P5 and P6. So it will perform a read operation for read P4, read P4, P5 and P6. Now in the situation that no switch amongst these 9 switches is pressed, the logic that will be returned on port pins P4, P5 and P6 will be a logic 0. Why? Because we have these pull down resistors. Now imagine that switch S1 is pressed by the user. So the moment switch S1 is pressed, because the subroutine is reading P4, P5, P6, not only will it read it once, it will keep on reading for some time. And the moment switch S1 is pressed, because P3 is also set to 1, P1 and P2 are also set to 1, it will return a value on P4 equal to logic 1. Alright, so P4, if S1 is pressed by the user, P4 is going to return a logic 1. However, if you notice, P4 is not only connected to one end of S3, it is also connected to one end of S2 as well as S1. Now it was S1 which was pressed, which made P4 equal to logic 1, but the microcontroller has no means of knowing whether it was because of S1 being pressed or S2 being pressed or S3 being pressed. And so it must do something to identify that what is the reason for P4 getting a value of logic 1. So what it will do is it will go through a sequence of operations. The first operation will be 1. It will set P1 equal to 1, P2 equal to 0 and P3 equal to 0. Now as you see, the moment P3 is set to 0, if S1 was pressed, it will make P4 equal to 0. But P1 is 1, but because S3 is not pressed, P4 is not going to be 1. P2 is 1, but because S2 is not pressed, P4 is not going to be 1, and therefore it would get P4. So in this situation, P1 equal to 1, P2 equal to 0, P3 is equal to 0. The value of P4 will return a logic 0 again. Then it will go to the next step of identification. It will do P1 equal to 0. It will reset P1 to 0. It will set P2 equal to 1 now, and it will retain P3 equal to 0. And then read P4 again, and because only S1 was pressed, the value of P4 will still return a logic 0. Then it will go to the third step, because there are only 3 combinations for P1, P2, P3. It is going to retain P1 is equal to 0. It is going to make P2 now equal to 0, and it will now set P3 equal to 1. The moment it sets P3 equal to 1 again, because S1 is pressed, the value of S1 will the value of P3 equal to 1 will come to P4 as 1. So now P4 will get a value of 1. The microcontroller will read that P4 is 1, and from here it will conclude that S1 was pressed. Now you see the human operation of pressing a switch versus the microcontroller's operation of performing these tasks. There is a huge difference of time. A human will press a switch and that switch press will last for several milliseconds or several hundred milliseconds, whereas the microcontroller can perform these tasks quite fast. And so even when the switch is just pressed, the microcontroller would have concluded that S1 has been pressed. However, it must wait for this switch to be released. So what it is going to do is it is going to wait, but before that, when you press a switch, as we have mentioned, there is a bouncing on the switch, so it has to debounce that switch. So it's going to delay, call a subroutine or delay subroutine for 1 millisecond. After that, it's going to wait for S1 to be released. And it may take any amount of time because people would they have different habits. Somebody may press it momentarily, somebody may press that switch for a longer duration of time. The microcontroller has to wait till such time that the switch is released. Then what it will do, it is going to again, when the switch is released, again the switch bounces, and so it must debounce it. So it's going to again call a delay subroutine of 1 millisecond, and after that it will check the value of P4 while P3 is still 1. P3 is 1, P2 is 0, P1 is 0. If the switch S1 is released now, P4 will return a value of 0. And so now it will conclude that yes, S1 was pressed and it has now been released. Now it has to send the value of a code so that the main program can be informed that it was switch S1 that was pressed. Now how will you indicate to the calling program? You will have to encode these 9 switches using a 4-bit switch code, and one of the values will be for S1 and so on. So 9 values will be taken using a 4-bit code. You can have 16 combinations, and out of these 9 will be used, the rest are not to be utilized, and so the main program will get the information that which of these 16 switches was pressed, if any switch was pressed. Now when you create a subroutine like this, this subroutine can be written in 2 forms, and now I am therefore talking about the software aspects. Any subroutine such as this, which is going to be used by the microcontroller to read external inputs, can be written in 2 forms, and they are called blocking subroutine or the same subroutine can be written as a non-blocking subroutine. What is the difference? In a blocking subroutine, here when the subroutine is called, the subroutine will not return till activity is detected, which means if I call a read keyboard subroutine, if I design it to be of the blocking nature, till a user presses a switch, it is not going to return to the main program. What will be the return value of such a blocking subroutine? Only a switch code number which would indicate which switch was pressed. But why is it called blocking? Because it blocks the performance or blocks the operation of the main program. Sometimes this may be a desirable method of writing a subroutine, but in the case of keyboard, this may not be a very good way, and instead we write the subroutine in a non-blocking format. Now a non-blocking subroutine would have 2 return values. First value will be, one of the values will be switch code, and let me not say that, let me say that the first value will be true or false, and the second value will be switch code. What is the interpretation? So, when the non-blocking will wait for a default amount of time for the user to press a switch. If during that time the user does not press a switch, it will return to the main program with the one of these values set to false to indicate that no switch was pressed, and in fact there is a timeout, and the value of switch code will be ignored by the main program. On the other hand, if during the default time, that is the time for which the subroutine is going to wait for the switches, if during that time which we call as the timeout period, within the timeout period if a user presses a switch, then after it has detected which switch was pressed, the subroutine will return the true and false value equal to true plus the switch code. So, the main program, when it calls a read keyboard subroutine which is written in a non-blocking format, when the subroutine returns, it is going to first check the value of this true or false return value. If it is set to true, then it will understand, it will know that a switch was pressed, and it will find out which switch was pressed by looking at the switch code. And this is the most common method of writing a subroutine for a switch matrix. Imagine if the switch matrix, such a switch matrix was used in an ATM machine, and if it was written in a blocking subroutine method, it is going to block that resource completely, because suppose you insert your ATM card into the machine and you refuse to enter your passcode, the machine is going to wait till you enter it. So, this is not a very advisable method, and you would notice that when you use a ATM machine, when you insert your ATM card, it asks you to enter your PIN number. If you do not enter your PIN number for a specified period of time, the ATM machine returns your card and says timeout. This is why, this is the reason, this is to indicate that the subroutine for the keypad on the ATM machine was written in the non-blocking fashion. And so, we will see in our subsequent lectures, we will show you how to write this non-blocking subroutine for a switch matrix if you would like to interface. Let us go to the next aspect. Now, we have seen that using a switch matrix you can connect several switches to your microcontroller system. There is one more interesting method of connecting multiple switches, and in fact using even lesser number of pins. In the first configuration you saw that you could connect one switch per pin. In the second configuration, creating a switch matrix, you could connect multiple number of switches to a few number of pins, but here is an alternative method which uses a single pin. However, that pin should have the capability of reading analog voltages. So, modern microcontrollers, as we know, have, if this is MSP 430 and similar microcontrollers, if this is MSP 430, which as you know has several ADC inputs. Using one of the ADC inputs, you can connect, as I have shown here, you can connect 4 switches, but there are some additional hardware required, as in this case we need 4 additional resistors, and let us say we decide the values of these 4 resistors to be equal values, and let us say the values are R1 equal to R2 equal to R3 equal to R4 is equal to 10 kilo ohm each. Now, how is the system going to work? You are going to write a subroutine where you are going to continuously sample the ADC value. Now, when no switch is pressed, what will be the ADC voltage? Will be, because of the pull up resistor, it will read almost VCC, which means the ADC will have a maximum count. If it is a 10-bit ADC, which MSP 430 has, then you can expect that the count on the ADC will be about 1023 or near about that value, or 1024. Now, if S1 is pressed, because the other side of S1 is connected to ground, it will give a 0 volts on the ADC. So, you would know if the ADC input is 0 volts, if the ADC input is more than 1000, that means no switch is being pressed. If the ADC input is near 0 volts, that is count near 0, a few numbers, that means S1 was pressed. On the other hand, if S2 is pressed, the voltage at this junction, the ADC input will be half of VCC, because all these resistors are equal. So, you can expect VCC being 3 volts, VCC is 3 volts. So, you will get about 1.5 volts at the ADC input. So, the corresponding count corresponding to 1.5 volts you can expect. So, when you get 1.5 volts, you can conclude that S2 pressed. If on the other hand S3 is pressed, that means this part of the resistor R3 is grounded, that will give a voltage at the ADC input which is 2 by 3 of VCC. That means you are going to get roughly 2 volts, that means S3 pressed. Similarly, if I press S4, it is going to put a ADC value equal to 3 by 4 of VCC, which is about 2.25 volts. And so, if you read a ADC count corresponding to 2.25 volts, then you conclude that S4 is pressed. And of course, here also you will have to debounce, and perhaps you could connect a capacitor from here to this, so that it will filter the ADC input, and it may also be used for debouncing the voltages because of the switches being pressed. But you can still add a delay and then wait for the ADC values to stabilize to conclude whether S1 is pressed or S2 is pressed or S3 is pressed or S4 is pressed. And you can extend this technique, but you may not be able to connect too many switches, because the entire range of the ADC, in this case 10 volt, the 3 volt range has a count from 0 to 1, 0 to 3. As you add more and more switches, you would get a smaller range of numbers. And in fact, using equal value resistors of 10 or whatever kilo ohms each is also giving you a non-linear counts, meaning when switch S1 is pressed compared to when nothing is pressed, you get an entire variation from 3 volts to 0 volts, whereas when S2 is pressed, you go to half. As you see, the difference between the voltages here, this is less and even less and so on. And so, one method could be to appropriately select the values of R1, R2, R3, R4 to be non-equal values, so that you get a voltage range which is equal parts from VCC to 0. And yet one does not recommend this technique to connect more than 4 and 5 or maybe 7, 8, 10 switches at max. So, this is an interesting method to connect multiple switches on a single ADC pin of a microcontroller. Let us see what all we can do. Now, the next input device is a rotary encoder. What is a rotary encoder? Usually it is a knob, and this is how it looks physically, but electrically it has 4 pins. One of the pins is VCC, that means you have to connect it to VCC. Another is ground, and there are usually 2 outputs labeled A and B. What it does is, let us say this is the reference point of this rotary encoder. As you move it either clockwise or anti-clockwise, it would give you pulses on A and B outputs, and the rate of the pulses that you are getting will indicate that you are moving the rotary encoder fast. If the rate is slow, that means you are moving it slowly. So, let us say suppose this is the 360 degrees, that is one entire rotation is suppose this is a 4-bit encoder, that means you have 16 parts, which means for every how much is that, roughly 20 degrees, 25 degrees of rotation, it will give you one pulse. So, if you move this 25 degrees from the reference, it will give you one pulse, but you would not know have you moved it in the clockwise direction or anti-clockwise direction, and for that is the reason why these two outputs are provided. These two outputs are called quadrature phase outputs. Which means the pulses on output A and B are 90 degrees apart. Let us see how these pulses look like. So, I have drawn the two sets of pulses. These are the output on A and B. In one case this could be clockwise. Motion of the encoder may give you this relationship between A and B. As you see, if you consider the reference to be B, that means during the time that B is high, A is going from 0 to 1. So, by measuring the relative phase of A and B, you can know that the rotary encoder is being moved in the clockwise direction. How many times, what angle it has moved, each pulse. So, each of this pulse, each of this edge indicates that it has moved about 20 degrees, 25 degrees as the case in this case of 4-bit encoder. However, if now the rotary encoder is moved in the counterclockwise direction, now you see for the same reference of B, the signal on A is a falling edge. So, you have to see whether during the time that B signal is high, does the A signal have a transition from 0 to 1, that means it goes in the clockwise direction. If it is going from 1 to 0, that means it is going in the counterclockwise direction. The angle will be measured by how much angle the encoder has moved will be measured by counting these pulses. So, in the software, in the microcontroller, we will have to keep a count, and it can increment or decrement that count based on whether the encoder is moved in the clockwise or counterclockwise direction, and the number of pulses will decide whether the count goes up or goes down depending upon whether it is moved in the clockwise or counterclockwise. This is the anti-clockwise direction. So, this is one of the popular inputs with which users can interact with the microcontroller system. Now, let us see how we can connect some output devices to our microcontroller system, and these would form from the output box, and we see the ways, multiple ways in which a microcontroller can interact with the outside world would be through LEDs of various types. As we had listed in that block, you have LEDs, normal LEDs, you have RGB LEDs, you can also have addressable RGB LEDs, you have 7 segment displays, you have dot matrix displays, LCD, and through sound output. Other outputs could be to control relays and motors. You would like to control heaters or a Peltier module with which you can heat or cool. You may want to control the speed and direction of a DC motor as well as a stepper motor. And so, in this session we are going to in this part of the lecture we are going to consider how to control LEDs to begin with, and then we will see how we can control relays, how we can control Peltier modules and DC motors, and so on. We will resume this lecture, this discussion in the next lecture. Thank you very much.